Hi, thank you for your interest in our paper. In the field of neural architecture search, or NAS, people aim to design algorithms to find the top performing networks on each dataset. From the past research, we know that datasets have some innate commonalities, and these commonalities have enabled transfer learning of neural networks across datasets. For example, we can directly deploy an ImageNet classification top performer to COCO detection and still receive pretty good results. This implies that there is room for studying how network design knowledge can be efficiently reused. NAS typically requires a large amount of computing resources, and it would be nice if we can find a way to reuse this critical information. Let's take a look at the existing solutions. We notice that many current methods do not explicitly look for general design patterns. Many algorithms focus on acing one single dataset, and when they face multiple datasets, they need to discard everything and search again. Some propose to transfer top architectures directly from one dataset to another, but this might be suboptimal. Some of them also impose assumptions on the search space, such as requiring one to be differentiable. We hope to create a more robust algorithm that can base its policy on some network design pattern and transfer such policy across different tasks. The problem is, can we pre-train a search policy on a task first and then transfer it to another one? It's a valid idea, but it might not be the best one since the pre-train and the target task can be quite different, so the search policy might not generalize well. We probably want to add a mechanism that uses dataset properties to adjust our policy. In our paper, we borrow help from a context-based meta-reinforcement learning approach, PEARL. To avoid confusion, we use the word task to refer to problems that share the same action space but differ in their reward distributions. Our searching agent contains three components: a context encoder, an RL controller, and a network evaluator. The encoder is the core of the design, and it aims to encode task-specific properties and guide the search. The catcher will first go through a meta-training phase, which involves many meta-training tasks. These are tasks that can be cheaply evaluated, so we can present the encoder with a diversified pool of tasks within limited time. The encoder is encouraged to consistently encode meaningful information for different tasks. Then, the pre-trained catcher will be deployed on the target task for fast adaptation. Let's look at the framework of our method. As we just mentioned, the encoder is responsible for providing information about the current task. The controller samples networks based on its search policy, and the evaluator will predict the performance of the networks and select the most promising one for training. To start the search, we randomly sample a network and put it into the search history. We are using the network reward pair as an important source of task information. It's a little bit tricky here because an intuitive choice to encode task properties is to encode from its own images, like using a ResNet to get representations of the images in a dataset. But it will be a little bit problematic when we are searching on, say, COCO detection and COCO segmentation tasks. The images are essentially the same, but the task has changed. So we instead think the network reward pairs might contain more general information. It provides flexibility to include tasks from different domains, and people can tweak how they want to define the reward as well. For example, the reward can be a function of a network's accuracy and inference time if the network's speed becomes critical. We denote the inferred task property, or the latent context variable, as Z. We model the distribution over Z as a multivariate Gaussian distribution with diagonal covariance matrix. The encoder network F takes in the network reward pair from the search history, and we denote the pair as C for context here. It will output the predicted mean and variance given every piece of context. Since the pairs are independent on the task, we could take their product and get the joint belief on the task representation. We end up with the posterior distribution, and from this, we sample the latent context Z. After we get the encoded latent context, we pass it to the controller. It's an RL agent using proximal policy optimization for update. We sample candidate networks from the controller, and these networks will be passed down to the evaluator. The evaluator takes in the context Z and encodings of the candidate networks and output their predicted performance scores. The network with the highest predicted score will be sent for training. The validation performance of the network will be used as the reward and will be stored in the search history along with the model's architecture encoding. In our algorithm, we go through this process for every meta-training task, and it's also repeated when it's adapting towards a target task. That was the forward pass of our method. Now let's take a look at how it's updated. The controller loss is the typical PPO loss. For details of PPO, please refer to the original paper. The evaluator loss is the Huber loss over its prediction and the actual reward. Since in the inference process of the encoder, we use an amortized variational inference approach. From the mathematical derivation in Perl, the evidence lower bound of the encoder is any objective plus the KL divergence between the latent context posterior and its prior. The KL term serves as a variational information bottleneck to avoid overfitting to meta-training tasks. So how does the encoder get updated? If you still remember, the encoder's output Z is fed into the controller and the evaluator as an input, so the gradients can be backpropagated to the encoder end to end. This Q phi Z given C and PZ are both Gaussian, with the KL term computed using their mean and variance. So here it's using the reparametrization trick for update. Let's take a look at the performance of catch under NASBench 201. This benchmark enables algorithms to compare fairly under the same settings. The meta-training tasks are constructed as sub-datasets of ImageNet, where we downsample the images to 16 by 16 and randomly take 10 or 20 or 30 classes. After 10 GPU hours of meta-training, catch meta performs exceedingly well on the datasets. We performed 500 trials of experiments, and each trial contains 50 search epochs. We report the validation accuracy of the best architecture found within 50 epochs. The results are sorted here. We can see tremendous improvement when catch is meta-trained. Here's the result comparison with one-shot algorithms averaged over 3 runs. Again, catch shows superior performance. NASBench 201 is a cell-based search space, and we also tried the ResNet search space, where the agent decides the base channel, network depth, the number of stages, when to downsample the images, and when to double the channels. Here's the result of the ImageNet adaptation. We use a combination of accuracy and inference time as our reward to search for networks that are both top-performing and time-efficient. The catch nets are discovered within the first 10 epochs of adaptation. We can see it's excelling in both accuracy and latency. We also conducted experiments on Cocoa and cityscapes. This is done under a more challenging setting, where the meta-train tasks only involve classification tasks, but we are adapting it to object detection and semantic segmentation to search for the backbone. Here are the results, and this is a first attempt to transfer such a search policy across different vision domains, and we look forward to more work on this line in the future. For ablation studies and further details, please refer to our paper. Thanks a lot.